Welcome to this scientific exploration of metacognition, the extraordinary ability to think about your own thinking. This is one of the most powerful cognitive tools humans possess. Let's begin by defining what metacognition actually is from a neuroscientific perspective. Metacognition is defined as the awareness and regulation of one's own cognitive processes. It's essentially your brain's ability to monitor, evaluate, and control its own operations. Research identifies two core components. First, metacognitive knowledge, which is what you know about how you think. Second, metacognitive regulation, which is how you control and adjust your thinking processes. Here's a conceptual model. The innermost circle represents metacognition, monitoring the cognitive processes in the middle layer, which interact with the external environment. Notice the bidirectional arrows showing the continuous feedback loop. Now, let me pose an important question. Why did metacognition evolve in humans? What evolutionary advantage does it provide? The answer lies in adaptive flexibility. Metacognition allows humans to adjust strategies in real time when facing novel or complex problems that have no pre-programmed solution. It enables learning from mistakes through mental simulation rather than through potentially fatal trial and error. You can think about what went wrong and adjust your approach. Additionally, metacognition facilitates social cooperation. By understanding your own mental states, you can better predict and understand others' mental states, what we call theory of mind. Let's examine the neural basis of metacognition. What happens in the brain when you engage in metacognitive processes? Research using functional MRI has identified key brain regions involved in metacognition. The prefrontal cortex at the front monitors and controls cognitive processes. The anterior cingulate cortex detects conflicts and errors. The posterior parietal cortex integrates information and maintains awareness. The prefrontal cortex, particularly the dorsolateral regions, is crucial for executive control and active monitoring of ongoing cognitive tasks. The anterior cingulate cortex specializes in error detection and conflict monitoring. It signals when something doesn't match expectations, triggering metacognitive evaluation. Fascinating studies by Fleming and colleagues have shown that individual differences in metacognitive accuracy actually correlate with gray matter volume in these specific brain regions. Now let's break down the metacognitive process into its operational components. How does this system actually work in practice? The metacognitive loop consists of three primary phases. Planning, where you set goals and select strategies. Monitoring, where you track progress during task execution. Evaluation, where you assess outcomes and adjust future approaches. This forms a continuous feedback cycle. In the planning phase, you activate relevant prior knowledge, set specific goals, and select appropriate strategies based on task demands. This is prospective metacognition, thinking ahead. During monitoring, you continuously assess whether your current approach is working. Are you making progress? Do you need to adjust? This is concurrent metacognition, happening in real time. In evaluation, you retrospectively analyze what worked and what didn't. This creates learning that feeds back into future planning. This is retrospective metacognition, learning from experience. Here's another important question. Can we actually measure metacognition scientifically? How do researchers quantify something as abstract as thinking about thinking? Yes, we can measure metacognition through several validated methods. Let me explain the primary approaches used in cognitive science. One method uses confidence ratings. After making a decision, subjects rate their confidence. We then calculate the correlation between confidence and accuracy. This measures metacognitive sensitivity, how well you know when you're right or wrong. Researchers use signal detection theory to calculate meta-D prime, a measure of metacognitive efficiency. This quantifies how well your subjective confidence matches your objective performance. Another method uses feeling of knowing judgments. Before attempting to recall information, you predict whether you'll be able to retrieve it. This measures prospective metacognitive accuracy. Think aloud protocols involve verbalizing your thought processes during problem solving. This provides rich qualitative data about metacognitive strategies, though it can interfere with the task it's. Now let's explore why metacognition is considered a cognitive superpower. What practical advantages does strong metacognition provide? Metacognition enhances four critical domains. Learning becomes more efficient because you know and what you need to study. Decision-making improves because you can evaluate the quality of your reasoning. Problem-solving gets better because you can detect when you're stuck and need to change strategies. And you become more adaptable because you can flexibly adjust to new situations. First, metacognition dramatically accelerates learning. Students with strong metacognitive skills learn material faster and retain it longer because they actively monitor comprehension and adjust study strategies. Meta-analyses by Hattie and colleagues show that metacognitive interventions produce effect sizes of 0.5 to 0.7 standard deviations. This is among the strongest effects in all of educational psychology. Second, metacognition improves decision-making. By monitoring your confidence calibration, you can identify when you're overconfident or underconfident, leading to better judgment. Metacognition helps reduce cognitive biases. When you're aware that you might be susceptible to confirmation bias or anchoring effects, you can deliberately counteract these tendencies. Third, metacognition enhances problem solving. Expert problem solvers spend more time on metacognitive activities like planning and monitoring compared to novices who jump straight to execution. Fourth, and often overlooked, metacognition supports emotional regulation. By recognizing your emotional states and how they influence thinking, you can manage stress and maintain focus under pressure. The exciting news is that metacognition is not fixed. It can be systematically developed through specific practices. Let's examine evidence-based techniques. First, implement self-questioning protocols. Before, during, and after tasks, ask yourself specific questions. What do I already know? What's my strategy? Is this working? What would I do differently? Structure your self-questioning into 3 temporal phases. Before the task, activate prior knowledge and plan. During the task, monitor progress and adjust. After the task, evaluate outcomes and extract lessons. Second, engage in deliberate practice with immediate feedback. The key is not just practice, but practice combined with accurate feedback that allows you to calibrate your confidence judgments. Third, externalize your thinking through thinking aloud or journaling. Making thought processes explicit enhances awareness and allows for systematic reflection. Fourth, conduct systematic error analysis. When you make mistakes, don't just correct them. Analyze why the error occurred and what misconception or flawed strategy led to it. Now for a critical question. Are there limits to metacognition? Can you think too much about your thinking? Yes, metacognition does have important limitations. Understanding these boundaries is crucial for applying metacognition effectively. First, the introspection illusion. We have limited conscious access to our own cognitive processes. Much of our thinking happens unconsciously, and introspective reports can be inaccurate or confabulated. Second, cognitive load. Metacognitive monitoring consumes working memory resources. If a task is already demanding, adding metacognitive activity can impair performance rather than enhance it. Third, analysis paralysis. Excessive metacognitive rumination can lead to overthinking, indecision, and decreased confidence. Sometimes you need to trust your intuition and act. Fourth, the Dunning-Kruger effect. People with low confidence often lack the metacognitive skills to recognize their incompetence. This creates a double burden. They're unskilled and unaware of it. Metacognition operates differently across various cognitive domains. Let's examine how it manifests in different contexts. In mathematics, metacognition involves selecting appropriate problem-solving strategies, monitoring whether your approach is productive, and recognizing when you need to try a different method. In reading, skilled readers continuously monitor comprehension. They detect when understanding breaks down and employ fix-up strategies like rereading or seeking clarification. In memory tasks, metacognition involves accurately assessing what information you've successfully encoded and what you still need to study. This is called metamemory. In reasoning and judgment, metacognition helps detect logical errors, identify cognitive biases, and consider alternative explanations. This is metacognitive debiasing. Let's look forward at emerging research directions in metacognition. Where is this field headed? First, deeper investigation of neural mechanisms. Advanced neuroimaging and computational modeling are revealing how metacognitive signals are generated and integrated in the brain. Second, artificial intelligence and metacognition. Can we create AI systems with metacognitive capabilities? Some researchers are developing self-monitoring neural networks that can assess their own confidence. Third, comparative studies across species. Do animals have metacognition? Studies with primates and dolphins suggest some animals can monitor their own uncertainty, raising fascinating questions about consciousness. Fourth, clinical applications. Metacognitive deficits are implicated in various disorders, including schizophrenia, obsessive-compulsive disorder, and depression. Metacognitive therapy shows promising results. Now let's create a practical framework for implementing metacognition in your daily life. This is how you actually harness this superpower. Here's a 4-stage implementation framework. Set explicit goals with clear success criteria. Plan your strategy in advance based on task analysis. Monitor your progress continuously with checkpoints. Reflect on outcomes and adjust your approach for next time. Step 1. Create a learning journal. After each significant learning session or problem-solving attempt, write brief reflections on what strategies you used and how effective they were. Step 2. Practice prediction and checking. Before solving problems or reading material, predict how difficult it will be and how well you'll do. Then compare predictions to actual performance. Step 3. Teach others. Explaining concepts forces you to monitor your own understanding. If you can't explain it clearly, you don't understand it well enough. This is the protege effect. Step 4. Schedule regular metacognitive reviews. Set aside time weekly to analyze your learning strategies, identify what's working, and experiment with new approaches. Let's consolidate the scientific evidence that makes metacognition truly a superpower. The evidence is compelling. Metacognitive ability correlates 0.4 to 0.6 with academic achievement across multiple studies. This is stronger than IQ for predicting long-term success. Metacognition distinguishes experts from novices across domains. Chess masters, physicians, and programmers all show superior metacognitive monitoring compared to less skilled practitioners. Metacognitive training enhances transfer of learning. Students who learn metacognitive strategies can apply knowledge more flexibly to novel situations, the ultimate goal of education. Critically, controlled experiments show metacognition improves with training. This isn't just a fixed trait. It's a skill that responds to systematic development. Let me synthesize the key insights from our exploration of metacognition. First, metacognition is a real, measurable cognitive capacity with specific neural substrates. It's not mystical or vague. It can be studied scientifically and improved through training. Second, metacognition operates through a recursive loop of planning, monitoring, and evaluation. Understanding this structure allows you to systematically engage these processes. Third, strong metacognitive skills predict success across diverse domains from academics to professional performance. It's a domain, general cognitive tool. Fourth, while metacognition has important limitations like cognitive load and the introspection illusion, these can be managed through strategic application. In conclusion, metacognition represents one of the most remarkable features of human cognition. The ability to step back and observe your own mental processes creates a powerful feedback loop for learning and adaptation. Think about the profound recursiveness here. Your brain is using itself to monitor and improve its. This self-referential capacity is what enables human intelligence to be so flexible and powerful. By developing strong metacognitive skills, you transform learning from a linear process into an exponential one. You learn how to learn, creating compound returns on cognitive investment. The practical message is clear. Start implementing metacognitive practices today. Question your thinking. Monitor your strategies. Reflect on your learning. This is how you unlock the superpower. As we've seen, the ancient maxim should be updated. The unexamined life may not be worth living, but the examined thought is definitely worth thinking. Thank you for this exploration of metacognition.